Hello, my name is Trevor Witt, and this is the video about using photogrammetry methods for road and bridge inspection. It's important to say for this video that during my time at Kansas State University, I developed a 3-day short course all around using drones for mapping missions. And so in this short 15-minute video, I won't be able to cover all those topics in much detail, but again, hopefully I'll give you the general overview of things to consider and be aware of when using your drone for mapping. A basic outline is looking at the basics of photogrammetry, some of the benefits and limitations. Again, knowing your why behind why you want to collect the data, key components of sensor settings, flight settings, and spatial control, and processing and analysis. So I'm not going to read through all of that because you can pause the video and see it, but photogrammetry is essentially using 2D images to then create measurable 3D models and maps. So it's this method of using software and using multiple angles of 2D images to create these geospatial products. Photogrammetry is helpful in that it is a passive remote sensing technique. So it's using ambient light to capture the data around you as opposed to an active technology like LiDAR. The benefits of this is you're able to measure objects, particularly change over time. So mapping an area and seeing how it changes, and not only seeing the change, but also being able to measure it. And photogrammetry methods are less expensive, have less expensive sensors as compared to LiDAR, and an order of sometimes 10 times less expensive. But photogrammetry is data heavy. It requires many images. It requires the expertise of collecting and also processing this data. It's reliant, again, on ambient conditions. So if it's dark outside or if it's close to sunrise or sunset, you're not going to collect as good a data as a bright sunny day around noon. It has difficulty with water and highly reflective surfaces. And you're always going to have some issues if there's movement within the area of interest. So in this case, with road and bridge inspection, if you have cars traveling beneath, you might get an artifact of that moving car within your data. So what do you want from your data? Why do you need to map it? I always point people towards using the most simple data collection techniques first and only jumping to more complicated things like photogrammetry and LiDAR if it's absolutely necessary. So think about why do you need to do this versus just taking photos or videos? Most likely your reasoning is going to be the ability to actually perform measurements on the data. And photogrammetry is able to produce a variety of different data products, which include orthomosaics, digital elevation models, and from that, tins, triangulated, like irregular networks, meshes, and then also point clouds. In more detail, orthomosaics are a geometrically correct image. So this is an image where you can perform distance measurements. It's where you hear the term orthorectified. This is a raster file format, typically a TIFF, typically containing red, green, and blue pixel values, so you can visualize it just like you are able to visualize the world. In contrast, a digital surface or elevation model is a raster file where instead of visual information, it contains elevation or height information. And this distinction between surface models and elevation models is a surface model contains the height data of everything within that mapped area, versus an elevation model is something that you're able to generate after some filtering where you're removing objects, trees, buildings, things like that, to where then you're getting a bare ground surface. So that's important to note if you ultimately want to generate some sort of vector file type like a contour or something like that. And then point clouds are also able to be generated from photogrammetry data. This is exactly the same type of file as is produced from LiDAR data. So what do you want out of it? What's the subject area that you're mapping? So thinking about as a road surface, bridge surface, and conversations with some of the counties a part of this project that are interested in measuring the volume of stockpiles. So that could also be a use case. And think about who are the stakeholders involved, who's collecting the data, who's the engineer on the project, How's management potentially going to be involved? Just making sure everybody's having a conversation about how the data is collected and how it will ultimately be used. Things you need to think about is how much detail do you want? This is measured as ground sample distance, or GSD, which is typically measured in inches or centimeters per pixel. This means a 1 inch per pixel. Every inch or every pixel represents a 1 by 1 inch square in the real world. The smaller this value, the more detail you're collecting. But beware of too much data. Drones are able to collect very detailed imagery. So sometimes you're actually collecting an unnecessary amount of detail that's just burdening your storage, burdening your processing. So just be mindful of how much detail do you actually need to make your ultimate decisions on the data. And again, this also applies. It's always better to collect a little bit more than what you need, but you don't want to collect so much that you've hit a point of diminishing returns. It's also important to think about how accurate your data needs to be. How accurate in reference to the real world or to potentially engineering drawings or things like that. Does it need to be accurate? What I said was to the real world, or to point to a specific location, or does it need to be just accurate within itself? Does the scale just need to be accurate? Because then those are different techniques you can use to achieve those things. This is a good general image, kind of just showing what GSD looks like, all the way from half meter to 80 meter pixels, and the ability to see that detail, and as that detail changes. So spatial control, what I was just talking about, is how accurate or what kind of accuracy do you need? So there's different ways to achieve it. There's this airborne control, or in other words, geotagged images, where in the metadata of your image is a GPS location. Almost all drone imagery has non-corrected GPS information, so that's going to be accurate to within 3 meters or so. Then you have different corrected variants, which use a differential GPS technology, either real-time kinematic, RTK, or post-processing kinematic, PPK. The difference between these two is just when the corrections are occurring. Real time means exactly that. Those corrections are happening in real time via a base station that's in a fixed location, typically set up over a benchmark or known coordinate, and it's broadcasting those corrections to the drone, correcting the airborne control in real time. Post-processing kinematic does that just on the post-processing side. So there's no real-time connection to the drone, but the base is set up close to your home location and is able to provide those corrections. You can do this with local bases, or if you have a base station network in your area of operation where you're able to use like an in-trip correction, that is also possible typically with this technology. Also depends on your specific equipment. Then there's scale bars. So you could use scale bars within your mapped area, something of a known length, and then you can measure this length in your data and see how close it is. So all of this data comes down to how much you trust it, or how much the decision maker trusts it. So it's up to you to think about how much of these or these different techniques and the way you evaluate it to enable a certain level of confidence to say, yes, this data is accurate to a certain level. Ground control points are points that are identifiable on the ground, used to reference your data. Checkpoints are used just to validate accuracy. So they are not used to influence the data. They're just a verification point. And these are typically, again, identifiable points surveyed by GPS equipment. For some further research, check out the American Society for Photogrammetry and Remote Sensing Positional Accuracy Standards for Digital Geospatial Data. That's a mouthful, but they've got a pretty extensive scientific standard related to this. Be mindful of your sensor settings. Again, typically auto is fine, but you should understand shutter speed, ISO, and aperture. Understand how your camera is focusing, whether that focus is fixed, which is ideal for mapping photogrammetry missions, but you could allow for some adjusted focus throughout the flight. White balance, again, fix this to sunny or cloudy. This is often forgot about where it's left to auto. It can lead to some kind of splotchiness in your maps. Most equipment offers this difference between timed interval and distance interval capturing. I always lean towards distance interval because this triggers the camera based on distance traveled, which can change if you have strong wind conditions. Versus timed interval, that's triggering the camera once per second, for example, but that could lead to some issues if wind is pushing your drone and making it travel slower or faster. So I always use distance interval. And it's really important, look for a de-warping setting on your imagery. You always want to turn this off for photogrammetry projects. You don't want the drone to be modifying your image in any way. You want that to be handled by the photogrammetry software. Some camera specifications, you need to be aware of the sensor size, the lens, fixed focal length that's critical for photogrammetry missions. You cannot use a zoom lens for photogrammetry, or really you could, but you don't want to change the zoom throughout the flight. That's bad. That prevents the photogrammetry software from being able to model the distortion of the lens. So you want the focal length to stay the same throughout the flight. You'll also see this term between rolling shutter and global shutter, sometimes called mechanical shutter. This is something I personally have a beef with. People say mechanical shutter when they mean global shutter. And the reason why I have a beef with that is this now pretty old YouTube video by the slow-mo guys. Really interesting, but that shows the difference between rolling shutter and global shutter. And so I encourage you to take a look at that. Ideally, you're using a global shutter. It's okay to use a rolling shutter because a lot of the photogrammetry software has corrections for this. Also think about your write speed. You just want to use high quality SD cards so that it's able to keep up, especially for large mapping missions, that it's able to write those images in time and not have any skips in your data. The layout of your flight settings. So this is specific to the mission planning applications with your equipment. I'm aware that sometimes you buy a drone and this is a paid feature, which is unfortunate because there's many drones where the mission planning or being able to fly this lawnmower pattern is just built in. You're able to use it from buying the equipment. But the lawnmower patterns where you're flying back and forth, the camera points at a 90-degree angle straight down. The term is nadir, or NADIR. Flies back and forth, progressing through the area of interest. Super important, set that ending point of the mission as close to you as possible. So where the drone starts away from you, and as that battery goes down, it ends close to you. So when you're low in battery, you're closer than further away. And then for long linear missions with photogrammetry, this is probably the biggest limitation. Make sure you have at least 3 to 4 flight lines that are going parallel with the road. That's the most time efficient way to collect it. If you're just getting 1 or 2, you can experience some extreme distortion for long linear missions. If you want to be sure to avoid that, just fly it perpendicular to the road. It'll take longer to fly it, but you'll see less of that distortion from that long linear orientation of the mission. Typical overlap. Forward overlap, you're talking 70 to 80% in the image overlap. Side is 60 to 80. My preference is always flying a balanced overlap of 70-70, but if efficiency is of utmost concern, you can get away with 60% side overlap and 80% forward. Camera angle, again, in most instances, it's facing straight down. But if you want a more complete, and if your goal is to create a 3D model, you can add additional oblique or off nadir, so like a 45-degree angle or a 60-degree angle of the camera to capture your area of interest. This is most typically used for those stockpile measurements where you're flying around in a circle around the stockpile, capturing those angles. Some settings for your altitude and speed. Your altitude directly impacts the ground sample distance of your data. Higher is less detail, lower is more detail. and you have some efficiencies for flying higher. Note your height above takeoff location versus elevation following. So if you're mapping a roadway where you have a lot of elevation change, like you're in the Flint Hills for something here in Kansas, you may want to use a setting in the drone. A lot of drones have the setting called elevation following, where it's going to track that elevation of the ground. This is really important for extreme elevation changes. Flying faster results in faster data collection, which makes sense, but there's some considerations. You can overwhelm the write speed, which can lead to gaps in your imagery. Flying too fast, if you don't have a fixed focus on your lens, it can lead to focus issues where that autofocus is trying to catch up. And you can also have motion blur issues, particularly at low altitudes and in darker ambient conditions. So if you have an overcast day and you're flying really low, try not to fly too fast because of that motion blur. And you can see some of those causes of motion blur right there. Again, be aware of these safety settings, being aware of the obstacles around you. Typically these missions you're flying at least 100 feet, so you're away from obstacles, but you can also have nearby radio towers and things like that to be aware of. Always be aware of your return to home settings and weather and airspace. In data validation at the field, I always like to have a laptop to where I can pull up the images, back them up right away, look at the exposure, look for motion blur and focus, try to identify any data gaps, and then eventually when you process back at the office, getting some sort of processing report. Speaking of processing, typical photogrammetry software uses a process called structure from motion. Two leaders of this are Pix4D is the company. Their legacy software is Mapper. Their new version is Matic. And then there's Agisoft Metashape. There's also a handful of other ones, but really these are the two main ones. They both have different cost tiers. They also provide cloud processing services if you don't want to invest in your own software. But processing it on your own, really typically just you need a good gaming laptop. Something $1,200 to $1,500 is a good starting point. The specifications that are minimal are shown on the website of these providers. There's a lot of other service providers that you can see here, and some of these software programs have other internal capabilities for analysis to export in your familiar file types in GIS or AutoCAD software. Then what can go wrong? As I've seen throughout the years, images being too dark or bright, exposure issues, blurry issues, things being out of focus, not crisp. And then you can always run into spatial control issues such as GPS errors or coordinate system errors. It's things to be aware of. And with that, that concludes this video about using photogrammetry for road and bridge inspection.